Okay, section 17.6, finding the hydronium ion concentration and pH of strong acids and weak acid solutions. So in a solution containing an acid, there are actually two potential sources of the hydronium ions. One, of course, is the ionization of the acid itself, and that's most likely going to be the big one. But we also have hydronium ions from the autoionization of water. We can usually ignore the autoionization of water in all but the most extremely dilute solutions. So a lot of times we just need to find convenient things to ignore, make our lives easier. So a strong acid, by definition, will ionize completely. So therefore, the concentration of hydronium ion in a strong acid is equal to the concentration of the strong acid. So if we look at 0.1 molar HCl solution, this is a strong acid. And so all of the acid ionizes to form hydrogen ions, hydronium ions, and chloride ions. And none of this is left. So if we start out with 0.1 molar HCl, we end up with 0.1 molar H plus, 0.1 molar Cl minus, and then the pH would be 1. Weak acids, calculating hydronium ion concentration requires us to solve an equilibrium problem. So we're going to use ice tables again. And here HA is representing our weak acid. This is the hydronium, and this is the conjugate base of that acid, or the anion. So starting out, we're going to give the concentration of the weak acid, and we're going to say that the initial hydronium ion concentration is approximately 0. It is not 0, of course. It's 10 to the minus 7, but generally we don't need to worry about that. Concentration of the anion will be 0. And so then we have a change. The acid concentration will go down, hydronium and the anion will go up. We can get our equilibrium things here and use the acid ionization constant for that weak acid to find out what the concentrations are. So let's do an example. Find the hydronium ion concentration of a 0.250 molar hydrofluoric acid solution. So we have hydrofluoric acid, and that's going to ionize to form hydronium ions and fluoride ions. So the initial concentration for the hydrofluoric acid is the listed concentration. So that's 0.250 molar. What do we put for the concentration of the hydrogen ion? Approximately 0. So we say this is approximately 0. And the fluoride is going to be 0. Then we're going to look at how this changes as the solution comes to equilibrium. So the reaction can only go in the forward direction. So HF is going to change by minus X. H plus will change by positive X. And the fluoride will change by positive X. If we had coefficients, then those coefficients would be on those X's, right? If something was like 2 fluorides, then it would be 2X. But almost always when we're dealing with acids, the coefficients are 1, so that's kind of nice. So then the equilibrium concentration is the initial plus the change. So 0.25 minus X, this is 0 plus X, and 0 plus X. So the equilibrium constant expression for this acid will be the hydrogen ion concentration times the fluoride ion concentration divided by the acid concentration. So in terms of our x's here, we've got x times x, which is x squared, divided by 0.250 minus x. And that is going to equal the equilibrium constant, the acid ionization constant for this acid. So here we have one of those quadratic equations. Many times we can use the x's small approximation. I can't remember for this one if it works or not, so let's find out. If we use x is small, then what we say is x is small enough that when we subtract it from 0.25, it doesn't change anything. So then we have x squared is 3.5 times 10 to the minus 4 times 0.25, and to get rid of this, we take the square root of that. So this is giving me 0.00935. How do we tell if that's small enough? 5%. We're looking to see if it's 5% or smaller, or less than 5%. So this is the number it's being subtracted from. So to check if that's okay, we take our x and we divide by what it's being subtracted by. Subtracted from, sorry. And this is 3.7%, less than 5. So we can use that approximation. Any questions? It's important to really see how this works because we're going to be doing it a lot and we're going to be adding things to it. So if this wasn't like, cool, yeah, I got that, let's talk about it before we move on. Yeah?
Can you just go through why that x is 0?
Yes. So why did I make x 0? A lot of times x is small enough that if we subtract it from this number, it's not actually going to make any difference. So, if we take 0.25 and we subtract what we got there, 0.00935, we end up with 0.24065, which is not the same as 0.25, but it's probably close enough that it doesn't matter. The reason we would want to do that is it makes the calculation a lot easier because then we can just solve for x. We don't need to use a solver or a quadratic equation. It is always okay to use a solver and get the actual correct answer. Any other questions?
Is it okay to use Desmos in case we don't know how another way?
Yeah, you could use Desmos or Wolfram Alpha or something on homework. But you need to be able to do something on your own for an exam. So I will not make you solve a quadratic equation on an exam. So if you don't have a calculator that can do those things for you, then you do need to learn how to do the x is small approximation.
Are you going on the exam? Will you have something that says use x is small?
No.
Oh.
No, I won't tell you to use x is small. Okay, so here's another one. Find the pH of a weak acid solution. Find the pH of a 0.0150 molar acetic acid solution. Ka is 1.8 times 10 to the minus 5. So on that last one, I used the actual formula for hydrofluoric acid because it's nice and short, right? But acetic acid is HC2, H3O2, and there's just all of this writing that I don't like doing. So this is where I'm just going to call it HA. So we have HA is in equilibrium with the hydrogen ion and A minus. I'm going to do initial change equilibrium. So this is the initial concentration, 0.0150. And what do we put for the hydrogen ion? Approximately 0. And for A, that's going to be 0. You know, if you don't write the approximately signs there, I'm not going to mark your work wrong. It's just that you do science for a while and you get very accustomed to being very precise about what you say. And so I cannot bring myself to say that it is 0 because I know that it isn't 0. So then the change here, this will go down by x, and these will go up by x. So 0.0150 minus x, x, and x. And for almost, well, actually for all of these weak acids, the equilibrium constant expression is very simple. And so this is going to be, again, x squared over 0.0150 minus x. And that's going to equal 1.8 times 10 to the minus 5. In the previous example, we successfully used x as small, but the starting concentration was larger. It was 0.25, and this is 0.015. And that time, it was just barely small enough. It was 3.7%. My guess is that this time x is not going to be small enough. That's just my guess. So let's try x is small. So if we do x is small, then we have x squared over 0.0150 is equal to 1.8 times 10 to the minus 5. So I'm going to take that result and divide by 0.015 and multiply by 100. And, cool, it's only 1.5%. So I was wrong. So the x is small approximation is valid here. When we do x is small, anywhere that x's are added or subtracted, we get rid of them. We make them 0. We say, well, this is small enough that we can consider it to be 0 when we're adding or subtracting. It's like having a whole semi-load of oranges, right, and weighing it at the scales, and then you throw a couple more oranges on top. Does that really change the mass in a significant way? No, it doesn't, because you put maybe an extra pound on there, and you're, measuring the whole load in tons, right? You added some, but it was so small that it doesn't really make any difference. So that's the idea with x is small. We can't make all of them 0, though, because here, x is not added or subtracted to anything. X is a number. And if we make all of them small, then we end up with no answers. not good. So this X that I found, what does that represent, and how's that going to help us find the pH? Yeah, so this is a molarity. And see right here? This is the equilibrium concentration of hydronium ion. So that's what we need to find the pH. So the pH is equal to the negative log of the hydrogen ion concentration. So negative log 0.0005196. And, you know, always a good idea to include a couple of extra digits. So negative log 0.0005196. So sig figs in Chem 1B are not as clear cut as they were in Chem 1A. But we want to just try to stay in the spirit of the significant figures rules. We don't want to overrepresent or underrepresent the precision of the answers that we're getting. So I would look at this and say, well, this concentration has 3 significant figures, but my equilibrium constant only has 2. And so it's very reasonable to say that this pH should have 2 significant figures. So it's going to be 3.28. Just calling it 3 is not precise enough. Saying, well, it's 3.284330858. Okay, nobody can even measure it that precisely. Any questions? Yes? So for pH, because it involves the logarithm function, when you take the logarithm of this number, the digits before the decimal point end up being the place-holding zeros. So if I wrote this in scientific notation, it would be 5.196 times 10 to the minus 4. This 3 comes from that 4. So this part of the number shows up before the decimal point, and this part here is after the decimal point. And I won't try to trick you with that, but you should, try to do it. Any other questions?
It's 2 sig figs because of the 1.5.
No, because of the 1.8, equilibrium constant. That's usually what's going to limit things. Yep. Any other questions?
So if I solve for x without using x is small, is that wrong?
No, it's not.
Because I got a very similar answer. It was 3.29
Okay.
when I did it.
Yeah, so 3.29, using a solver instead of the x is small approximation. So we should understand about significant figures that the last digit in a properly recorded number is uncertain. So if there's a little difference of 1 or 2 in that last digit, we'd say those numbers are essentially the same. Yeah. Excellent. Anybody else? .28. So this one's telling us when x is small doesn't work. So here we have a 0.01 molar nitrous acid solution. We had a Ka there, 4.6 times 10 to the minus 4. Let's find the pH. Okay, so we're gonna make an ice table. So HA in equilibrium with H plus and A minus. Initial change, equilibrium. Here's our initial concentration for the acid, 0.010. Hydrogen ion approximately 0. That anion is 0. And then we look at the changes. So that reactant is going to lose X, and the products are going to gain X. So we end up with 0.010 minus X, X, and X. And so we can say, well, the equilibrium constant, 4.6 times 10 to the minus 4 is equal to the concentrations of the products, so X squared, divided by the concentration of the reactant, which is 0.010 minus X. So let's use the solver, since the question told us, right, that it's the X is small isn't going to work. So I'm going to plug in X squared, and in the denominator, 0.01 minus X. And over on the right side, 4.6 times 10 to the minus 4. My calculator has a number solver and a polynomial solver. The polynomial solver would work as well, but what I like about the number solver is I don't need to rearrange that equation at all. I don't need to set it to 0. I can just type it in the way it looks and say, hey, what's X? And this is telling me that X is 0.001927. If we look at that to see what percentage of 0.01 that is, we see that it's actually 19%, so way above the 5%. So that is equal to the hydrogen or hydronium ion concentration at equilibrium. So then to calculate the pH, it's the negative log of the X that I just found. So 2.7151, we're going to call that 2.72. I'm going to keep 2 decimal places because my equilibrium constant had 2 significant figures. Any questions? .72. Okay.
For that one,
Uh-huh.
when I plugged it in, it kept giving me like sign change error.
Okay.
How do you?
I will show you how to fix the sign change error problem. So this problem's a little different. This one's giving us the concentration of a weak acid and telling us what the pH is and saying find the acid ionization constant, find Ka. Well, let's just think about this. We don't know what the acid is, so this is the perfect time to use HA for our acid. So we know that HA is in equilibrium, the hydrogen ion concentration, and A minus, and we're going to have initial change in equilibrium. 0.175 represents what? The initial concentration of the acid. What's the initial concentration of hydronium? About 0. And A minus? 0. They didn't tell us any different. If it was not 0, they would tell us. Okay, so what can we figure out from the pH? The concentration of the hydrogen ion at equilibrium, that value down here. So the hydrogen ion concentration is equal to 10 raised to the negative pH. So that's 10 to the negative 3.25. So that needs 2 significant figures. I'm going to write down 2 more. I'm not going to put this in scientific notation because there's 3 zeros, and my brain can see 3 zeros without counting them. When you get more than 3 zeros, they start to swim around, and then scientific notation might be best. But scientific notation is kind of tedious at times. So that's the equilibrium concentration for the hydrogen ion. Now, it doesn't always fit real well into the table. So we've got the same sort of change thing going on here. We're going to lose X here, and we're going to gain X here, and we're going to gain X there. But now we know one of the answers. So in this column, this is kind of like what happened in that last experiment. We've got an initial concentration of 0, a change of X, and we know that's equal to this number. So then X is this number, right? So then over here for A, its equilibrium concentration is also that. Maybe stick it down here so it looks like it's in the right place. And then over here, 0.175 minus X. I should have made this bigger. So that's 0.175 minus 0.0005623. Zero 0.17444. That's what that equals. So these are my product concentrations. That's my reactant concentration. Ka equals that product concentration squared, because these are the same, is this times this, divided by that. And that's one where I would put it in scientific notation because I actually have to get my Apple Pencil and count those zeros. 1, 2, 3, 4, 5. Any questions? Good question. Why only two significant figures? The pH, it's the digits after the decimal point that are significant figures. So this pH has two significant figures.
Okay.
And that's where this is coming from. In my book, it's always okay if you have too many significant figures, because it's really easy to round them off, right? Not having enough can end up giving you an actual wrong answer. Any other questions? (1.8 times 10 to the minus 6). So this is a conceptual one. The initial concentration and Ka of several weak acid solutions are listed. For which solution is the excess small approximation least likely to work in finding the pH? I heard C, and I believe that's correct. We need X to be small relative to that initial concentration. So here, the initial concentration is large, and so a small x doesn't have to be terribly small. Here we've got 0.1, here's another 1 molar. This is the smallest initial concentration. And this is also the larger of the Kas, which means that X is going to be larger to start with, and then you're subtracting it from a smaller number. So large K and small concentration, X is small is probably not going to work. Any questions about that one? So of these guys, which solution is most acidic? Meaning which one has the lowest pH? It is A. Why? Strong acid. Yep. So HCl is a strong acid, meaning all of the molecules turn into hydrogen ions and chloride ions. And so we'll have a hydrogen ion concentration of 0.1. HF is a weak acid. Here, the concentration is twice as big as that, but this is a weak acid. It only ionizes a little bit. So the strong acid is going to be the most acidic there. So we can look at percent ionization of a weak acid. So this is telling us what percent of the acid is ionized. The amount ionized is going to be equal to the hydronium ion concentration at equilibrium. And the total amount of acid present is the initial concentration of the acid. So it's the hydronium ion concentration at equilibrium divided by the initial concentration times 100. And we find that the percent ionization is relatively small for weak acids. For strong acids, it's essentially 100%. Find the percent ionization of a 0.250 molar acetic acid solution at 25 degrees Celsius. Ka is 1.8 times 10 to the minus 5. So percent ionization is going to equal the hydronium ion concentration at equilibrium divided by the initial acid concentration times 100. So guess what we need to make? A nice table. I don't know what that was.
Try to make a nice table.
So we have our initial concentration of 0.250. Hydrogen ion concentration starts out at approximately 0, at anion concentration is 0. Reactant loses X, products gain X. So down here, 0.250 minus X, X, and X. So 1.8 times 10 to the minus 5 is our equilibrium constant. It's going to equal X squared divided by 0.250 minus X. If we use X as small, let's see what we get. .002121. And I'm going to check that. Divide by 0.25 times 100. That's 0.8%. So X is small. So solving for X, X is that hydronium ion concentration that we need. So percent ionization is the 0.002121 divided by 0.250 times 100. .8% of the molecules are ionized. So if you have 100 acid molecules, less than 1 is ionized. These ionize just a little tiny bit. Any questions?
So for 6-6, on that, would you go out to 3 because of the polarity?
Yeah, on this one, I'd probably go out to 3 because I'm dividing by this. Well, but this is really only 2. So, I mean, we could argue it either way, 0.848 or 0.85.
Your slide says 0.85.
Yeah, it probably does. Any other questions? So if we look at weak acids, if the concentration of the weak acid is increased, then the equilibrium concentration of hydronium ion also increases. That makes sense. What doesn't make so much sense is that the percent ionization actually decreases as the acid becomes more concentrated. So, oops. So here looking at nitrous acid, 0.2 molar concentration is 4.8% ionized, but a 2.5 molar solution is only 1.4% ionized. Well, how does that work? Well, if we think about this equilibrium, and we think about diluting the concentration, what that's going to do is it's going to force the equilibrium to the right because there's more moles of substance on the right. And so that will increase the amount of hydrogen ions. If we increase the concentration, it's going to shift this way a little bit, and that will go. I really don't like that explanation. I don't like that explanation. because this is an equilibrium that's governed by an equilibrium constant, if I double this concentration, I'm not necessarily doubling the concentration on the other side. Because H plus over A minus, H plus times A minus over HA is equal to a constant. If I double this, and this was doubled, that would change the equilibrium constant. Because this would be 2 and 2, that would be 4 times larger on the top and 2 times larger on the bottom. So the increase in the hydrogen ion concentration is not proportional. It's not a linear relationship. And that's why the percent ionization decreases as the concentration increases.
Can I say that one more time?
Yeah, I can say that one more time. We know that this equilibrium is governed by an equilibrium constant, right? And so we're at equilibrium. If I double the bottom concentration, that's not going to increase the top concentrations by twice as much. Because then that would violate the equilibrium constant. It wouldn't work. So if this goes up by a factor of 2, these are going to go up by a factor of less than 2. And so higher concentrations, the amount of hydrogen ion per initial concentration gets smaller and smaller. Yep. That's one of those things that is great if you understand that. If you don't, you'll be fine. If you can't do an ice table, we need to talk. There's a lot of ice tables here. Oops, gave away the answer. So which weak acid solution has the greatest percent ionization? It's all the same acid. You're looking for high concentration or low concentration? Low concentration. It seems backwards, but a low concentration has a higher percent ionization. What if we have mixtures of acids? Well, this could get complicated, but a lot of times the acids have significantly different strengths, and so we're able to ignore the weaker acid and just look at the contribution of the stronger acid. So if we look at a strong acid and a weak acid, so 0.1 molar HCl, 0.1 molar HCHO2, we don't need to know what that is. It's not one of the 6 strong acids, therefore it's a weak acid. So there's 3 sources of hydronium ions. There's some coming from the strong acid, some coming from the weak acid, and some coming from the autoionization of water. In the previous examples, just looking at the weak acid, we ignored the autoionization of water because the amount of hydrogen ion coming from the weak acid was so much bigger than 10 to the minus 7. Here what we're going to do is we're also going to ignore the contribution of the weak acid. So here's our HCl. That's strong, meaning it goes to completion. Here's our weak acid, showing its ionization. That's 1.8 times 10 to the minus 4. And the autoionization of water is 1 times 10 to the minus 14. What actually happens here, as this forms hydronium ion concentration, that's increasing the hydronium ion concentration here, which is actually shifting this equilibrium into reverse. And it'll also shift this equilibrium into reverse, because for these equilibria, if we add more of the product, it's going to shift to the reactant side. So that means that there's even less coming from the weak acid and from water. So those contributions are negligible. So we get Our initial hydrogen ion concentration then will just be from the HCl. And we can make an ice table to see what will happen with that weak acid. So initially we've got 0.1 molar hydronium ion concentration. That is from the complete ionization of the HCl. And then we have the initial concentration of the weak acid. The initial concentration of this formate ion is 0. Okay, so this equilibrium then the reaction can only go to the right because there's none of this anion here. So it can't shift to the left. So this will decrease, that will increase, and that will increase. The amount that this is going to change is going to be so small that it's going to be negligible. And you can do the calculation if you don't believe me. Any questions? What if we have 2 weak acids? Again, 3 sources of H3O+. We can't always ignore the weaker acid, but many times we can. So these are the conditions necessary to ignore the weaker acid and the ionization of water. If the Ka's of the weak acids differ by more than a factor of several hundred. So if they're like 10 to the minus 5 and 10 to the minus 6, they're close to each other, then we can't ignore it. But if one's 10 to the minus 3 and one's 10 to the minus 7, then that second one is not going to matter. We also need to have the situation where either the concentrations of the acids are similar or the concentration of the stronger acid is larger. Usually those 2 things work out. So this is asking us to find the hypochlorite ion concentration of a mixture that's 0.3 molar HF, and their Ka is 6.9 times 10 to the minus 4. And we have hypochlorous acid, 0.1 molar, and that Ka is 2.9 times 10 to the minus 8. So which is a stronger acid, HF or HClO? Okay, let's try that again. Which one of these is stronger? Which one has the larger Ka? HF is the stronger one. Okay. And then HF, the stronger one, also has a larger concentration than the weaker acid. My mind just went blank. I think this is what I'm supposed to do. So, got the HF. That's going to be the important one. That one's 0.3. This is 0, and that's 0. We got minus x and plus x and plus x. 0.300 minus x. We've got x and we've got x. So 6.9 times 10 to the minus 4 is going to be equal to x squared divided by 0.300 minus x. We'll take a chance that x is small. So if X is small, X equals 0.01439. Whew, that was a close one. 4.8%. So from our stronger acid, that's the concentration of hydrogen ion. So we're looking at the strong acid first. If we were just looking at what the pH was, we could stop and say, well, it's this concentration, find the pH. But they're not asking us about the pH, they're asking us for the hypochlorite ion concentration. So we're going to take this concentration of hydrogen ion as the starting concentration for that second acid. The starting concentration of the acid itself was 0.100, and the hypochlorite ion is 0. So that equilibrium constant, 2.9 times 10 to the minus 8, is going to be equal to this times that. Divided by 0.1 minus x. So how would we do x is small here? Anywhere that x is added or subtracted from something, we're going to say it's essentially 0. We're going to ignore it. So then 2.9 times 10 to the minus 8 times 0.1 divided by 0.01439. X should equal 2.0 times 10 to the minus 7. If I'm going to check my percentage for X is small, I want to look at the smallest one because that's going to give me the biggest percentage. Right, so I want to make sure that it's less than 5% of that guy, which I can tell you right now that it is. It's actually 0.001%. Questions? That's a step up from what we were just doing. Isn't it? What we're doing here is we're saying, okay, this is the strongest acid. It's going to have the biggest impact on the hydronium ion concentration. So I'm going to find out what it would give me if it was all by itself. And so I find this value. The weaker acid is going to contribute less, and this amount of hydronium ion concentration over here on the product side is going to reduce its effect even more. So this one will start where that one ended up. So that's our initial concentration. And so doing this, we can calculate what X is, which is the hypochlorite ion concentration. Now, if we put this X in here, To find the hydrogen ion concentration, is it going to change the hydrogen ion concentration? No, it isn't, because it's so small. No questions? I got it right. It's always nice. Okay, judging relative pH. Which solution is most acidic, meaning has the lowest pH? Is that going to be a 1 molar HCl solution, a 2 molar HF solution, or a solution that's 1 molar in HF and 1 molar in HClO? It's going to be A. Because this is the strong acid. This is a weak acid that's twice as concentrated. This is 2 different weak acids, total of twice the concentration of HCl. But the ionization of those weak acids is so small. It's like maybe 5%, right? Where it's 100% for the HCl. So the concentration of a weak acid has to be a lot larger than a strong acid to have a lower pH.